Two methods, two precise measurements, two incompatible results, one universe, and a growing suspicion that something, somewhere in our understanding of reality, may be fundamentally wrong. For nearly a century, astronomers have agreed on one monumental discovery. The universe is expanding. Since Edwin Hubble observed that distant galaxies are receding from us, the expansion of space itself has become a cornerstone of modern cosmology. But today, the very number that describes that expansion, the Hubble constant, has become the center of one of the greatest scientific crises of our time. The more accurately we measure it, the less the universe agrees with itself. And that disagreement is no longer small enough to ignore. Before we descend into this cosmic mystery, welcome to the channel. If you're fascinated by the deepest questions about space, time, and the hidden structure of reality, make sure to like this video and subscribe for more explorations at the edge of science. Here at Next Frontier Science, we go beyond the surface of discovery and into the ideas that may redefine our understanding of the universe. Today, we venture into one of the most unsettling and fascinating puzzles in modern cosmology, a growing crack in the foundation of the standard model of the universe. We will explore what scientists call the Hubble Tension, a discrepancy so persistent and so precise that it may be pointing toward new physics. Are we misunderstanding the expansion of the cosmos? Has something changed in the universe's history that we have yet to uncover? Or is there a deeper layer of reality still hidden from view? To answer that, we must first understand the number at the center of this debate. The Hubble constant, often written as h0, tells us how fast the universe is expanding today. It is expressed in kilometers per second per megaparsec, meaning how much faster galaxies move away from us for every additional megaparsec of distance. If h0 is 70 kilometers per second, MPC, then a galaxy 1 megaparsec away recedes at 70 kilometers per second. At 10 megaparsecs, it recedes at 700 kilometers per second. This number is not just about motion. It encodes the age of the universe, its size, its fate, and the relative balance of matter and energy that fills the cosmos. For years, cosmologists believed we were converging on a precise value. But instead of convergence, we found divergence. Two independent methods, each incredibly sophisticated, began producing answers that disagree far beyond their margins of error. And the more precise the measurements became, the worse the disagreement grew. The first method looks deep into the ancient universe. It relies on the cosmic microwave background, the faint afterglow of the Big Bang, emitted when the universe was only 380,000 years old. Satellites like the European Space Agency's Planck mission mapped tiny temperature fluctuations in this radiation with extraordinary precision. From those patterns, cosmologists infer the composition of the early universe and, using the standard model of cosmology, known as lambda-c/dm, extrapolate forward to calculate today's expansion rate. The result from Planck is about 67 to 68 kilometers per second per megaparsec. The second method looks not to the early universe, but to the nearby one. It builds what astronomers call the cosmic distance ladder. First, we measure distances to nearby stars using parallax. Then we calibrate Cepheid variable stars, whose intrinsic brightness correlates with their pulsation periods. Then we use those Cepheids to calibrate Type Ia supernova, stellar explosions so luminous they can be seen across vast cosmic distances. By measuring how bright these supernovae appear and how fast their host galaxies are receding, we derive the expansion rate directly. This method consistently yields a value around 73 to 74 kilometers per second per megaparsec. At first glance, the difference may seem small, roughly 5 or 6 kilometers per second per megaparsec. But in cosmology, this gap is enormous. The statistical significance now exceeds 5 sigma in several analyses, meaning the probability that this discrepancy is due to random error is extraordinarily low. In physics, 5 sigma is the gold standard for discovery. Yet here, instead of discovering a new particle, we may be discovering a flaw in our cosmological model. So who is right? Is the early universe telling the truth? Or are our local measurements revealing something new? The Planck satellite's data is astonishingly precise. It does not measure the Hubble constant directly. Instead, it measures the acoustic peaks in the cosmic microwave background, subtle patterns formed by sound waves, rippling through the hot plasma of the infant universe. These peaks encode the universe's matter density, dark matter content, and dark energy fraction. When fed into the lambda-c dm model, the equations predict today's expansion rate with remarkable consistency. The beauty of this method lies in its global coherence. Everything fits, if the model is correct. But the local measurements are equally impressive. Teams like SHOES, led by Adam Rees, have refined the distance ladder with exquisite care. They have improved calibration using the Hubble Space Telescope and now the James Webb Space Telescope. They have reanalyzed Cepheid variables in different galaxies. They have cross-checked with alternative distance indicators such as tip of the red giant branch stars. And the result does not move toward Planck. It stays high. This is not a matter of sloppy data. Both sides have scrutinized systematic errors. Both have attempted independent confirmations. And yet the gap remains, which brings us to a far more unsettling possibility. What if both are correct? If the early universe predicts one expansion rate and the late universe measures another, perhaps the expansion history is not what we thought. Perhaps something changed between then and now. Something subtle, something powerful. One possibility is early dark energy. In this scenario, an additional form of energy briefly influenced the expansion rate before recombination, altering the inferred parameters from the cosmic microwave background. Another idea involves new relativistic particles, additional neutrino-like species contributing radiation density in the early universe. Some propose interactions within dark matter itself. Others suggest that dark energy may not be a simple cosmological constant, but a dynamic field that evolves over time. There are even more radical ideas. Modified gravity theories question whether Einstein's general relativity holds perfectly at cosmological scales. Perhaps our understanding of how gravity operates across billions of light years needs refinement. Perhaps the universe is not perfectly homogeneous on the largest scales. Or perhaps unknown physics subtly shifts the calibration between early and late epochs. What makes the Hubble tension so profound is that it sits at the intersection of nearly everything we know about cosmology. The age of the universe, about 13.8 billion years, depends on H0. The density of dark energy depends on H0. The fate of cosmic expansion depends on H0. If this number shifts, the entire cosmic story must be recalibrated, and yet science thrives on tension. Historically, discrepancies have led to revolutions. The orbit of Mercury as perihelion did not match Newtonian predictions, and that anomaly led to general relativity. The ultraviolet catastrophe led to quantum mechanics. The acceleration of the universe's expansion led to the discovery of dark energy itself. Every major shift in physics began with something that did not fit. The Hubble tension may be the next crack in the foundation. Upcoming observatories may provide clarity. The James Webb Space Telescope is already refining Cepheid and supernova measurements. The Euclid mission and the Vera Rubin Observatory will map large-scale structure with unprecedented detail. Gravitational wave detections from neutron star mergers offer a completely independent method, standard sirens, to measure cosmic expansion without relying on the distance ladder or the CMB model. If these independent probes converge on one value, the mystery may narrow. If they deepen the divide, the implications grow even larger. Cosmology has humbled us before. We once believed the universe was static. We once believed we had mapped its structure completely. Each time, the cosmos revealed something deeper. Now we may be standing at another turning point. If the Hubble tension is real, then our model of reality is incomplete. And when reality refuses to match our equations, it's not the universe that needs revision, it's our understanding of it. The universe continues to expand, and with it, the boundaries of what we know. If you made it all the way here, you're already thinking beyond the surface. So like this video, subscribe, and join us as we keep exploring the questions that challenge everything we thought we understood. Because at Next Frontier Science, the edge of knowledge is just the beginning.